Welcome to Part 9, Continuous Exponential Growth Models. We began the chapter by looking at a simple exponential growth model, a times b to the x. In this section, we're going to look at a slightly different formulation, a times e to the b times x, where e represents the mathematical constant 2.718 and is the limit to the growth rate if measured in infinitesimally small intervals, as opposed to the once per day it is done now. So the way our model is currently formulated is that our growth rate, say it is 1%, will be multiplied by the previous day's value to get the current day's value, and then the next day's value will be retrieved by multiplying today's value by the same 1%. Well, we could think of coronavirus cases as growing in less than 1 day intervals. It could be 1 hour or 1 minute, and if we shrink these intervals so that they are infinitesimally small, then we get this formulation right here. So to sort of prove this to you mathematically, we can define a function here called grow, and we'll just keep the rate at 10%. And what we'll do is allow n to be the number of intervals. It will, instead of having just this 10%, what will happen is we'll divide it by n. So if it's 24, we'll divide it by 24, but then we'll raise it to the 24th power, and we'll get a number that's slightly larger than our original rate. So if we were to say n is 1, say once per day, well, this wouldn't change anything. We would still get a growth of 10%. So this is like assuming we start out with 1. Now we're at 1.1. But if we use 2 intervals, well, we now get 10.25, or instead of just 0.1. 5 intervals, 10, 100. So you can see they are growing, but the growth is sort of slowing down. And what happens is, as this number approaches infinity, well, we can just use this e and raise it to the power of our growth rate, and we will get what the limit would be. So that's where the mathematical constant e comes in to get continuous growth. So if we were measuring coronavirus cases like instantaneously growing at some certain growth rate, we would use this formulation over here, the continuous exponential growth. Okay, so let's go down here. And this bit of code will graph both the old formulation and the new formulation. So the blue line is the continuous growth of 10%. That means it is compounded, if you will. It's usually used in financial applications, but you can also think of it as growing continuously at a particular growth rate, as opposed to once per day. So you'll see the difference. They start out very similar, but then the continuous growth rate will be a bit higher. So we have this, and in the formula, the continuous growth rate will need to be subtracted by 1 from the original growth rate. So it's not going to be the same exact number. So if it's 1.1, we'll have 0.1 in the new formulation. So we can define a function that will be used to model our coronavirus cases. And like the simple exponential growth, we're going to have x as the first argument, and then all the parameters as the other ones. We have the same number of parameters here as the first formulation, just a and b. Then the body of the function will be slightly different. We're just going to use this NumPy exponential function, which uses the base of e and raises whatever you pass to it to the power of, or raises e to that power. So here we have b times x. Now we did all the hard work in the above in the rest of the chapter to come up with this predict all function. So this is a great function. All you need to do is change the model and give it bounds, of course, and also give it an initial guess over here as to what the values will be. And let's give it more than, so the initial starting rate, what does it say, is between 1 and 1,000. the growth rate will be between this number 0.001 and 0.1, and then here is our initial guess. So remember, we just give it all of this we talked about in the last video. We just changed our model. Of course, we have a slightly different bounds and a slightly different initial guess. And then let's look at the graph. So it produces a graph and returns two things. Let's look at the graph first. So the blue is actual, the orange is our model. Doesn't model it particularly well, but that's what we got. Now, if we look at the outputs over here from the function, this is the initial value, this is the growth rate, and here are the predictions for the daily cases. So it's great. This function is able to just take in any new model. As long as you can give it the bounds and initial values, then it will spit out something over here and produce a graph to see the results. All right, so that is our new formulation, continuous exponential growth model. So it gives you another sort of tool to use to model instead of just the basic formulation.